Hello, everyone. My name is Kohn Sham, a staff scientist here at QUICKLINKS Pleasanton. It's my pleasure today to introduce our speaker, Dr. Kate. Dip received his SB degree in chemistry and physics from MIT in 2016, where he was in Professor Troy Van Voorhees' group and got introduced to the world of orbital optimized DFT. He's currently a PhD candidate in Professor Martin Hedgwarn's group at UC Berkeley. He's interested in development of quantum chemistry methods and their application to problems of interest to the experimental community, with a specific emphasis on the use of DFT beyond ground state energetics. Without further ado, I'm going to turn this over to Dip.
All righty. Thank you for the nice introduction, Kohn, and thank you everyone for showing up bright and early in the morning, at least in my time zone, for this. As Kohn mentioned, I'll be chatting a little bit about using orbital optimized density functional theory, or ODFT, for electronic excited states. But before we go there, let me first explain why this is in any way necessary. When we, actually even before that, these are the 4 papers that I'll be talking mostly out of. So if you're short on time, maybe you want to screenshot those and take a look at them later if you can't stay through the whole presentation. Or maybe you're a type of person who likes to read more than listen. So anyways, as I mentioned before, I would like to motivate why we would even try to use something like orbital optimized density functional theory for electronic excited states. To do that, we should first take a step back and look at how we handle ground state quantum chemistry. Within ground state quantum chemistry, there's broadly speaking 3 types of methods that people tend to use most of the time. The first, of course, is Kohn Sham DFT, which is very, very popular, probably the most widely used electronic structure method till date, and is incredibly effective in practice for single reference problems, which is to say for cases where the total wave function is dominated by one single stated determinant. And if these single reference problems have low electron self-interaction or delocalization error, we can expect a modern Kohn Sham density functional to be pretty effective at computing the energy and ground state properties of this system. The great thing about KSDFT is that it's computationally inexpensive compared to the other stuff that are widely used, and therefore can be used for pretty large systems, such as this big organic molecule, where you really can't do much else. Other than DFT, people also use low-order couple cluster theory like CCSD, which is useful for a sort of Goldilocks zone in which the problems are not very multi-reference, but are also not fully single reference. This is most effective for moderately sized systems because these methods are pretty steep computational scaling. CCSD is n to the 6 versus system size n, for instance, and is perhaps the best way to go about things if delocalization makes DFT problematic. For problems that are absolutely multi-reference with lots of determinants entering into the wave function, people tend to use explicitly multi-reference methods like CF, DMRG, or selected CI, such as for this cobalt carbide molecule, which is adequately multi-reference to break even CCSD-TQ, and thus an explicit CI-based method is probably the best way to go about this. Exponential scaling of these methods limits applicability of this type of approach to small systems only. However, there's one thing that unites all of these 3 types of methods used for ground state calculations. All of them involve optimizing the orbitals to minimize energy at some level of the problem. For DFT, you just do it at the mean field level. For something like CCSD, you first do a Hartree-Fock optimization and then do CCSD on top of the optimized Hartree-Fock solution. Or for CF, you orbital optimize in the presence of explicit wave function-based correlation. Nonetheless, orbital optimization is a key feature for all of these ground state methods. Moving on to excited states, these tend to happen mostly because of excitations induced by light that are generally greater than 1 eV in energy, although there are exceptions, as always. These are pretty relevant for spectroscopy, photochemistry, or photo anything that really comes up. And when people try to model these electronic excited states for large systems, just like how Kohn Sham DFT is the normal route for large ground state problems, people use linear response time-dependent DFT or TDDFT for electronic excited states of large systems. There are some good things about this. It's very computationally efficient and is essentially black box. You ask for the lowest 50 routes, and chances are you'll at least get the lowest 5 routes correctly and a large number of other excited states in the process. However, TDDFT has some significant practical limitations that get in the way of it being universal. Basically, TDDFT tries to compute excited states from the linear response of a ground state Kohn Sham DFT solution to time-dependent electric fields. This is the inconvenient feature of magnifying ground state errors to catastrophic proportions. On the left, I have a case for charge transfer from ammonia to fluorine and the predictions for various functionals using TDDFT. As you can see that the different functionals give very different results, spanning from anywhere between 0 volts to 12.5 volts and are generally below the couple cluster benchmark. That seems to indicate that A, this method is somewhat unreliable because different methods are giving wildly different answers, and B, there is that the systematic underestimation seems to suggest that there is also some kind of a systematic problem going on in here. On the right, there's a much simpler case, just looking at the triplet excited states of stretched H2, where we can see there's a pretty nasty kink that shows up right at the Coulson-Fisher point, where the ground state switches from restricted to spin polarized. And it's almost as if there are 2 separate families of solutions that are being stitched together at the Coulson-Fisher point if we look at the TDDFT solutions. Now, this is kind of weird because while we know that ground state DFT is not perfect, it does not normally suffer catastrophes on quite that scale. That almost seems to argue that the problem here is not the DFT part, but is rather the linear response part. If we, could perhaps try to orbital optimize the excited state solutions instead of relying on linear response, we could probably get a good answer out of DFT. And this turns out to be the case. If we look at the ammonia fluorine problem again, we see that the charge transfer on the left-hand figure, we see that the charge transfer energies predicted by the orbital optimized delta SCF method are much more consistent with each other. There's no significant variation across functionals, and they agree with the couple cluster benchmark pretty well, in contrast with TDDFT, where there's both huge variation and large errors. Similarly, if we go back to the problem of stretched H2, we see that getting the lowest triplet state, which had a nasty kink in TDDFT, is pretty easy if we just set the multiplicity to 3 and try to do a standard UHF or UKS calculation. This basically seems to argue that having an orbital optimized route to excited states is going to be pretty effective at handling many of the problems that come up with TDDFT. And the fact that orbital optimization helps excited states is not exactly breaking news. It predates Kohn Sham theory by a number of years. The earliest reference I found to this was a paper by Mulliken in 1958, where he noted that the lowest excited state of H2 is Rydberg, and therefore it needs a much more diffuse orbital than the ground state orbitals. However, we also sort of know that TDDFT is the workhorse for excited state quantum chemistry. So why don't people orbital optimize everywhere? One of the problems is that if you want to optimize a given state, you first need to know something about that state. So we need to have some prior knowledge about the target state versus TDDFT, where we just have to ask for an arbitrary number of states and have the code compute them in a essentially black box fashion. That's, I don't think, a problem that can be addressed easily because, well, we need to know what we have to optimize before we can optimize anything. However, there are 2 other problems that I would like to talk about today. The first is the variational collapse problem, in that excited states are normally not minima of energy. They're in fact saddle points most of the time. Optimization efforts therefore often fail to stick onto the saddle point and instead slip onto a nearby minimum, like the ground state instead. So we need to have effective algorithms that can avoid the variational collapse problem. We also have a problem with multi-configurational character, in that excited states are rarely representable by single slated determinants. However, Kohn Sham DFT is a single determinant theory by construction, and so there needs to be some kind of a way to recombine multiple configurations into giving a single spin pure answer for an excited state. So we need some kind of ansatz to be able to recouple multiple determinants. And I would focus on the last two aspects of the problem. In fact, I would first like to talk a little bit about the ansatz, because as a quantum chemist at least, that's what I think people would be most interested in. What the simplest sort of ansatz for an excited state would be a single Slater determinant, just as in for the ground state. Electronic excitations often unpair electrons. However, if all the unpaired electrons have the same spin, such as the triplet state of helium on the left-hand figure, or if there is no unpairing of spin, such as this double excitation from the lone pair to the pi star orbital of formaldehyde, we can model the excited state with a single Slater determinant without any problems. In that case, we just need to optimize this non-alpha electronic configuration Slater determinant for such a state using Kohn Sham DFT, compute the energy of this determinant, subtract the ground state energy, and thus have the excitation energy. This method is called delta SCF because it effectively involves taking a difference between the self-consistent field energy of the excited Slater determinant and the ground Slater determinant. And this is a pretty old idea. There are references to this in the 1960s, probably even earlier if one were to take a much more careful look than I have so far. However, it's not really universally applicable. And a simple case where this is not correct would be to look at a low-lying singlet excited state of a closed shell molecule. If we do a single excitation of a closed shell molecule to a singlet excited state, we see that both the up and the down spins are equally likely to be excited, and therefore at least two determinants would be needed at all times. Any single determinant of the two given on the right would be a half singlet, half triplet mixture. And we have to figure out a way to recombine these two determinants to obtain a spin pure energy. The way people have done it is that they have noted that it's quite easy to get the energy of this mixed Slater determinant that's halfway between singlet and the triplet and call that energy EM. And similarly, it's easy to get the energy of the pure triplet because both of the unpaired spins are pointing in the same direction, and therefore the state is representable by a single Slater determinant, and call it triplet. We know that this mixed state is halfway between a singlet and a triplet, and so we can extract the singlet energy by just assuming that the mixed state's energy is the average of the singlet and the triplet using equation 1. So there are two ways one can go about using equation 1 to obtain singlet energies. The first would be to separately optimize the mixed state and the triplet state with delta SCF, and then apply equation 1 afterwards, which would be some kind of a projection after variation, and which we call approximately projected delta SCF, but it has gone by other names in literature as well. An alternative route would be to have one set of orbitals instead of separately optimizing states, and use that one set of spin restricted orbitals to optimize ES. This would be sort of a variation after projection method and is called restricted open shell Kohn Sham or ROCKS, first used in DFT by Frank et al. In 1998, although references with Hartree-Fock date back earlier into the 60s. But that's the case with two unpaired spins. If we have three or more, the situation gets much, much more complicated. If we had two unpaired spins, we only had a singlet and triplet to worry about, so we could just view this as sort of a spin projection based method. However, if we have more unpaired spins, we have a lot more states and a spin projection becomes much trickier. For instance, if we have four unpaired spins, the manifold of states would have one quartet, three triplets, and two singlets. And therefore, just trying to project out to the correct S-squared value is not going to be enough. What we can do instead is try to use some kind of a Heisenberg-like spin-spin coupling model, or Ising-like if that's the term you'd prefer, and hope that it yields at least a reasonable answer. The math for this gets complicated real quick. If you see the case for just three unpaired electrons, it's this pretty convoluted expression. And for four unpaired electrons onwards, there is no closed form solution to this, although numerical solutions are pretty easily obtainable. I would make a quick note that unlike ROCKS, which is directly implemented in QChem, equation 3 for the 3 unpaired electron case is not yet directly implemented, and anyone trying to use it would have to first just optimize M1, M2, and M3 energies with delta SCF, and then compute the energy manually afterwards. That being said, this is sorry, this recoupled delta SCF is a projection after variation method, and you can look at the references below for more details about its use for electronic excited states. So to summarize the ansatze that I quickly rushed over, for cases where all unpaired electrons have the same spin or there are no unpaired electrons, you can just approximate the excited state with a single Slater determinant and call that delta SCF. If you have a singlet state with two unpaired spins, then you need two determinants, and this can be approximated by either AP delta SCF or ROX. For more general cases needing greater than two determinants, can be approximated with recoupled delta SCF, which is projection after variation. One limitation to keep in mind about all of these methods is that they only work if the orbital occupations in the excited state are integer, which is to say orbitals have at either 2, 1, or 0 electrons. In other words, all multireference character in these excited states stem from the need to have spin purity. An actual multireference excited state in which some orbital has a population of 0.5, another has 0.25 or something like that, would not be tractable by these methods, just like a multireference ground state of similar character would be out of reach for normal DFT. And if you want to learn more about these ansatze, I would invite you to check out our perspective in JPCL from last year, which describes this in greater details. And for ROX at least, this section 7.8 in QChem's manual has more details about it. Moving on from the ansatze, we need to sort of figure out algorithms to run these ansatze with. And well, the first type of algorithm that people think of when it comes to running ground state DFT at least is self-consistent fields. The idea there involves solving the following eigenvalue equation, f of c times c equals e times s times c. This sort of an equation is generally solved following the Rutan procedure, in which you have a guess matrix of molecular orbital C, from which you build a Fock matrix as a function of that, and then diagonalize this Fock matrix to get eigenvectors. These eigenvectors become the new MOs, and you repeat the cycle till you have convergence. This sort of a Rutan cycle approach is typically accelerated with algorithms like direct inversion of iterative subspace, or DICE, which is at this point probably the most widely used algorithm for converging ground states. And it works pretty well for a lot of problems. If you just consider the case of H2, where at equilibrium geometry with B3LIP, it seems like DICE could converge the energy pretty quickly with 5 cycles. Seems to work great. However, there's one problem with it. There's no guarantee that a repeated diagonalization or self-consistent field method like this would ever converge. If instead of H2 at equilibrium, we look at H2 at 10 angstroms and try to converge a solution with DICE, we see that even after 1,000 cycles, it gets nowhere. It just keeps on oscillating about something like 0.47 and sometimes swings pretty wildly to positive values, but it doesn't actually converge. Because of that, we have some other robust approaches to get energies for such problems. And the best way to do this kind of a thing is via direct minimization of energy, in which the energy E is explicitly minimized via taking gradients, second derivatives, or things of that nature, versus the orbital degrees of freedom, theta. QChem has a number of these algorithms, but the most prominent of this is the geometric direct minimization, or GDM, developed by Troy Van Voorhis and Martin Hedgorden back in 2002. In theory, an approach like GDM should always find a solution if given enough cycles, although it might overstep or undershoot at times. But as you see for the H2 with the 10 angstrom stretch and B3LIP, GDM gets you a solution at 17 steps, a lot more than what DICE do for the equilibrium solution, but it manages to at least find something for the stretched case where DICE could not. I would make one quick note that DICE and GDM can, but don't always find the same solution in the case where both converge. However, a solution converged by one method should be stationary with respect to the other. It's just that both of these methods are searching for solutions within the total space of possibilities in different ways, and could, in principle, land on different solutions. But that was the ground state. And talking about algorithms that are good at minimizing energy. However, excited states, as I might have mentioned before, are saddle points of energy. So ground state algorithms tend to slip that down to a nearby minimum instead of remaining on the desired saddle. And this means that ground state solvers like DICE and GDM are quite unsuitable for excited state orbital optimization, as made clear by the attempt to converge an excited state of a boron atom on sending the 2p electron therein to a 3p level. We see that both the DICE and the GDM algorithms rapidly collapse back down to the ground state of the boron atom in this case, instead of converging to the excited state. This variational collapse problem is one that excited state ODFT development has to handle. And QChem has 3 approaches for doing this using self-consistent field methods. The classic being the maximum overlap method, or MOM, which was proposed by Gilbert, Besley, and Gill back in 2008. The idea there is that after each DICE step, instead of filling the orbitals resulting from the eigenvectors of the Fock matrix based on the Aufbau principle, AE, in ascending order of energy, you fill these orbitals instead based on their overlap with the previous set of orbitals, and thus minimize drift from the original set. This has worked for a large number of cases, but not always, and thus led to a more recent proposal from Peter Gill's group by Barker, where they proposed, instead of filling orbitals based on overlap with the previous set of orbitals, you just fill them based on overlap with the initial set at step equals 0 in order to prevent any drift whatsoever. This is called initial MOM or IMOM, and is also available in QChem. More recently, Kevin Carter-Fenk and John Harbert have proposed a state-targeted energy projection, or STEP, where the idea is to move unoccupied orbitals up in energy so that the occupied unoccupied mixing is reduced at each Fock diagonalization, slowing down the convergence and ensuring that the filling orbitals up by the Aufbau principle gives you the right answer. You can check out the manual for more details about these methods, but I would like to move on to something else. I'm a rather big fan of using GDM for ground state problems, so I wanted something that would work as an analog of GDM for excited states. AE used some kind of a direct minimization method. However, the energy is like the energy excited states are not energy minima in orbital space. So we need to use some kind of a different objective function. And the objective function we chose to use was this quantity delta, which is a squared gradient of the energy versus orbital degrees of freedom, theta. This is convenient because any stationary point of energy is a global minima of delta with delta equals 0. And any point with delta equals 0 is a global minima. So if we find some kind of an initial guess and minimize delta to 0 with very slow steps by following the gradient, we are guaranteed to land on the stationary point closest to this initial guess. And it can really be used with any quantum chemistry method, not just DFT. It can be used with orbital optimized MP2, CASA-CF, and so on and so forth, although we have focused mostly on DFT. As to how it works in practice, I go back to the case of the excited state of the boron atom, in which we see that the square gradient minimization, or SGM approach, manages to converge the 2p to 3p excitation without any trouble, unlike the classic ground state convergers like DICE or GDM, which undergo variational collapse. Now, I'll just give a quick overview of the math in here, I'd hopefully not bore you too much. The key points are just that the square gradient minimization preserves the computational scaling of DFT or TDDFT. Despite using this complicated squared gradient quantity, it doesn't actually increase the computational cost all that much. And that's because the gradient of delta is equal to the gradient of energy contracted with the Hessian of energy. Now, the analytic Hessian is often quite well known for DFT because it's used for TDDFT. But even if for some arbitrary quantum chemistry method, this analytic Hessian is unknown, the gradient of delta can be computed via finite differences from the gradient of energy by evaluating the gradient of energy at 3 points, as shown in equation 6. So the cost of evaluating the gradient of delta is between 2 to 3 times as much as evaluating the gradient of energy. And therefore, the ground state GDM DFT scaling is preserved. The QChem SVM code, in fact, is basically GDM, but with the objective function being changed from energy to delta in order to make sure that excited state convergence works. Now, SGM, despite all the positive things I've said about it, has a couple of limitations. One is that it's trying to minimize some kind of a squared quantity, and therefore the condition number of the problem gets a little worse. So you would typically need more iterations to converge an excited state than you would need to converge a ground state, which combined with the 2 to 3 times larger prefactor means that these calculations are somewhat more expensive than ground state calculations, although with the same computational scaling. The other problem is that you could in principle land on some kind of a local minima of delta with a non-zero value that are not stationary points of energy. However, this is extremely rare in practice. I think I've seen it like twice, and both of the times I'm still not sure if they were a real instance or a bug in the code for that particular version in time. But nonetheless, even if they were pretty prevalent, it does appear that excited state orbital optimization at ground state scaling is not a particularly bad thing. Hang on. Sorry for the mouse malfunction. Now, having talked a little bit about the ansatze and the algorithms to use with that ansatze, let me try to go to some of the applications to highlight why such methods might be useful. The first case is to see if they do any harm by looking at simple cases where we would normally expect TDDFT to do just fine. The cases in question would be 104 excitations in small molecules like formaldehyde or thiophene, for which very highly accurate reference values at FCI or at least CCSD full triples level were computed by Luce et al. For their mountaineering datasets. My friend Hongzhou Ye from Troy Van Voorhis group computed the error in rocks versus their benchmark values and compared against some well-regarded wave function theories like CISPR-ND or CC2 for the dataset. It seems like rocks with the modern omega V97 X-V functional does pretty well, having an RMS of 0.24 EV for this 104 singlet excitations of small molecules, which is slightly better than CISPR-ND, CC2, or ADC2, although they are basically all within the same ballpark. Significantly worse than CCSD, but considering that one of them has a n to the 4 scaling versus the other n to the 6, that's a trade that I am generally quite prepared to make. That being said, these are very simple cases where we would normally expect TDDFT to work just fine, and it only serves to show that ROX doesn't degrade performance significantly in this regime if it does so anything at all. A more interesting case would be double excitations, like an excitation from the lone pair of formaldehyde going to the pi star level, or pi to pi star double excitation in ethene. These double excitations are absolutely inaccessible to TDDFT and represent a major challenge for couple cluster methods. You can see here in this figure that the n to the 7 scaling couple cluster CC3 method, which has an RMS error of something like below 0.1 EV for single excitations, has something close to a 1 volt error for most of these double excitations, as given by the pink bar in the figure. However, delta SCF for ROX is astoundingly accurate for these excitations, as made clear by the error bars in there. In fact, if we just look at the RMS for a benchmark set of double excitations, also computed by Luce et al. Using high-level multireference theory, we see that CC3 has an RMS error greater than a volt, whereas even LDA, the uniform electron gas functional, the simplest one of them all, is about half of that. And a modern functional like SCAN or PB0, or even a classic like PB0, can bring it down to something like 0.2 or 0.3 EV. So if you are trying to model some kind of a doubly excited state that is in principle well representable by a single slater determinant, the way to go would be to use some of these delta methods instead of attempting to do high-level couple cluster theory. Another case where TDDFT is generally considered to be deficient is charge transfer, specifically long-range charge transfer, as I mentioned before for the case of a charge transfer from ammonia to fluorine. The long-range charge transfer problem at its most elementary level is just a function of combining together the ionization potential of the donor, the electron affinity of the acceptor, and the electrostatic interaction between the charged entities. DFT can handle all of those three terms well, so an orbital optimized model should be adequate. And indeed, it seems to be the case for this ammonia-fluorine long-range charge transfer, where the two molecules are separated by 1,000 angstroms and an electron transferred from the lone pair of ammonia to the antibonding level of fluorine, where all of the orbital optimized delta SCF solutions agree fairly well with the CCSD parenti benchmark. Whereas TDDFT is abysmal, it can literally give you any value you want based on exact exchange. A great way to make theory and experiment agree, just start tuning the amount of exact exchange in your functional. That's a long-range charge transfer problem. In shorter-range charge transfer, the TDDFT errors are somewhat less dramatic, although still pretty significant. As the shorter the range of charge transfer goes, the more valence character it starts to have. However, ROX or delta SCF remains the more effective tool for modeling such short-range charge transfer as well, especially if you're interested in something like a singlet triplet gap between a charge transfer singlet state and the corresponding triplet, such as ones that are of relevance for thermally activated delayed fluorescence, in which you have intersystem crossing between the singlet and triplet due to the small energy gap between them, which can just happen from thermal energy. Back in the day, I had computed the errors in emission energies of these systems, emission energies of systems that exhibit TDDF with B3lib and PB0 using both TDDFT and ROX for the emission energy and the singlet triplet gap, and found that ROX gave much lower errors than TDDFT for both of those properties. More recently, Kunze and Mills, along with co-workers, had put out a very nice JPCL article in last year for a recent treatment of TDDF with ROX and singlet ROX and solvent effects, which I encourage you to check out if you're interested in using these kind of methods to look at charge transfer excitations. There's one other regime in which using orbital optimized methods confers significant advantages, and that is core level spectroscopy. In core spectroscopy, we are trying to tickle inertial electrons with X-ray or XUV radiation and either ionize them or excite them to some high-lying unoccupied level. This is a very convenient way to probe atom-specific local environments because the inertial electrons are not really involved with bonding. However, linear response methods like TDDFT don't really handle the relaxation of the density in response to the core hole formation properly, and therefore they wind up having something like a greater than 10 eV error, as shown for a case of 40 excitations out of 1s orbitals of small molecules for atoms like carbon, nitrogen, oxygen, and fluorine, and where we can see that TDDFT with a broad spectrum of functionals ranging from PBE to Hartree-Fock and has an RMS error greater than 10 volts. However, ROX seems like something that can handle this because it does orbital optimization. It should be able to handle the core hole formation problem pretty effectively, and indeed it seems to do pretty well. It's a dramatic improvement over TDDFT to the point that the solid bars showing the RMS errors for ROX are pretty hard to see versus the full size of TDDFT errors. So maybe it's a good idea to just zoom in and focus on the ROX errors alone. And we see that there's some pretty broad spectrum of values based on what functional is employed. But the encouraging thing is that SCAN and Omega B97 X-V do very well, predicting core excitation energies to about 0.2, 0.3 V RMS for these 40 excitations out of 1s orbitals with small molecules. This is pretty good because these are compared against experiment, and the experimental uncertainty in the data itself is about 0.1 eV. So you can argue that that SCAN with ROX is functionally semi-quantitative in yielding these K-edge excitation energies. Similar accuracy is also seen for excitations out of 2p levels of silicon, phosphorus, sulfur, and chlorine, the so-called L-edge. And this seems to argue that this is a pretty effective way of finding core excitations. However, I've only talked of energies so far. How about a complete spectrum? To do that, let's first take a step back and look at what would be the previous state of the art, which would be the specially trained short-range corrected SRC1R1 functional which was trained in order to have much smaller error than the 10 eV errors that we've seen before, that I had shown before with TDDFT. We see that it gets something semi-reasonable for thymine, but the quality of the spectrum is not that great in comparison to experiments. If, on the other hand, we just look at the rock scan spectrum, we see a much better level of agreement. The largest error is for the highest energy peak, and that is of the order of 0.3 eV, which is not that much in the scale of the uncertainties associated with experimental energies themselves. And keep in mind that this result was obtained using a local meta-GGA like scan, as compared to a range separated, a hybrid functional like SRC1R1. So the actual computational scaling of this problem is lower, because we can use a local functional instead of a hybrid. We could also look at some more complicated systems like radicals and see how well our approach for recoupling 3 electrons work for predicting the spectra of open shell systems. And we considered the case of the allyl radical, for which high quality experimental spectrum was available. And we see that the prediction is pretty decent. It's not perfect by any means. The first peak is blue shifted by the recoupled scan a bit relative to the vibrationally resolved structure in the experimental spectrum, but the higher energy peaks align pretty well. And it's not that bad really in comparison to equation of motion couple cluster singles and doubles. For a more extreme case, we could quickly look at a simple looking molecule, CO+, whose experimental spectrum was measured very recently. And we see that all of the theoretical methods have some trouble in reproducing experiment. If recoupled scan gets the features qualitatively right, but the positions of the peaks could certainly be better. However, it's a great improvement over equation of motion couple cluster, which gets the positions and the intensities completely wrong. Just gets a qualitatively wrong spectrum. This is in large part a consequence of the recoupling approach, ensuring spin purity in the solutions and optimizing the density in response to the core hole formation, which a linear response method like CCSD can't do. So this is basically an example where the cheaper method is able to get a better answer by taking advantage of the right physics for the problem. So far, I'd only talked of light elements like carbon, oxygen, nitrogen, and such. We have recently been able to look at heavier elements as well. The reason why we didn't do that before was that 1s excitation or ionization energies for anything heavier than neon has a greater than 1 volt relativistic contribution. However, we have been able to implement the X2C model for scalar relativistic corrections into QChem, thanks to my amazing coworker Leo Cunha and Richard Kang and Yuji Bao. Please check out our preprint here if you're interested in the details. But by using this X2C model, we can compute 1s excitation and ionization energies of elements as heavy as chromium, and find that similar errors as the light elements appear. Like for the case, there's a Boxen error plot for the excitation energies for heavy elements like sulfur, chlorine, phosphorus, and silicon predicted by scan, and we see that it's again in that 2.3 eV band for these, similar to the light elements. On the right, there's a combined emission and absorption spectrum for the CSO for the sulfur KH of the CSO molecule, where again we find good agreement between the computed spectrum and the experiment, indicating that this is a pretty good approach for computing such things. Okay, I've droned a lot about what the methods are and how good they might be, but I guess one of the things this audience really cares about is how to use them. And I would like to spend the last few minutes trying to do this before I completely run out. Within QChem, and I'm speaking to the best of my knowledge here, the available features are that you can do delta SCF with MOM, IMOM, STEP, or SGM. However, the spin purification or recoupling has to be done by the user at present. You just get single determinant energies that have to be manually recoupled afterwards. If you don't want to do manual recoupling and you're only interested in singlets with 2 unpaired electrons, you can always do ROCks, which is indeed the recommended method for such problems, using SGM or STEP. Analytic nuclear gradients are available for both delta SCF and rocks. Analytic frequencies are available for delta SCF when the ground state analytic frequencies are available for that functional. However, if you want rocks frequencies, you have to get them with finite difference at the moment. Transition dipole moments are also available for both delta SCF and rocks. I'll show you how to get them in a second. The X2C model is also available for all kinds of DFT. However, it's only available for single points at the minute. There isn't any, we haven't yet been able to add the gradient or Hessian for those. All of this is already written up in the manual, so in case anyone wants to take a look afterwards. So if we are trying to do some kind of an ODFT calculation for a problem, what would we need? Like, I'm being a little facetious here, but we would need the ansatz. We need to figure out which one are we going to use, delta SCF or rocks, which variant of it, restricted, unrestricted, blah, blah, blah. Then we would need to pick a functional, like always. And here the choices are a little bit different for the ground state. Omega B97 M-P is an excellent functional for doing any kind of ground state energy calculation, but it might not be the best choice for excited states as it was not trained on those at all. So something more minimally parameterized like scan or B3lib is likely a safer choice because they probably are less likely to deviate from ideal behavior as they have much fewer parameters. Then we would need to pick an algorithm depending on your taste for whether you like repeated diagonalization, for which you could go to MOM or STEP, or do square gradient minimization if you are like me and love GDM type direct minimization approaches. If you're trying to use SGM, you should just specify SCF algorithm to be SGM if you're doing a restricted open shell calculation, and SCF algorithm SGM LS for a restricted or plain restricted or unrestricted calculation. The difference just stems from the GDM algorithm these are based off on, and it's just internal details. And finally, you need some kind of an initial guess to decide which state you're going to be converging. And this is generally achieved by reading in orbitals from a previous job, often the ground state, and then specifying what sort of a non-alpha configuration your state will have by using the occupied section for a restricted or unrestricted calculation, or the reorder MO section for a restricted open shell calculation. As you can see, there's some differences very qualitatively between doing a restricted open shell calculation and just a plain closed shell restricted or unrestricted calculation. And as for an example, let's first consider a delta SCF, a restricted delta SCF calculation, going from representing the double excitation from the 2s to the 2p levels for beryllium. We see that with scan, converging the ground state with dice is pretty simple, 7 steps and done, nothing too sophisticated. Then we read in these ground state orbitals as shown by SCFS read for the excited state calculation, in which the input is very similar to the one before, except that this time the SCF algorithm has been specified to be SGM-LS, and there is an occupied section that says that you're reading in the orbitals from the previous job, but you're occupying the first orbital, AE, the 1s orbital, and the third orbital, which is the 2p, which is one of the 2p orbitals for this excited state, and you're leaving the second orbital, which was the 2s orbital in the previous job, empty. And with this, you ask SGM to run. It prints out the delta value at each step to corresponding to the squared gradient, and after 10 steps, it converges onto an excitation energy in good agreement with the benchmark value with Luce et al. Now that was a delta SCF example. Let me just give a restricted open shell Kohn Sham example of this. This corresponds to an excitation out of the 1s carbon 1s orbital of formaldehyde to a 3p level. Like before, we converge a ground state solution, and you will notice one interesting thing about this calculation is that it uses a mixed basis set instead of just the plain CCPV-TZ used for the beryllium atom. We can use a mixed basis set for such problems because the core excitation is local, and therefore we only need to provide a high quality basis for the atom of interest, namely carbon here, where we have provided a triple zeta, and we can go cheap and just use a plain simple double zeta basis for other atoms. This Since we are using this mixed basis, we don't have a normal superposition of atomic density of SAT gas available. So it's best to specify SCF gas autosat so that it quickly converges the ground state calculation. And you should also, if you're interested in transition dipole moments, you should add a transform save so that it saves a copy of these ground state orbitals separately for computing the transition dipole afterwards. Using these ground state orbitals, we can compute the core ionized state by using mostly the same input as before, except we specify that this is a restricted open shell calculation with ROSCF true. We specify the SCF algorithm SGM for the excited state calculation, and we have SCF gas read to read in the previous orbitals. Since this is a carbon 1s, we are ionizing out of the second orbital from the previous job, and so we reordered the MOs such as the second orbitals pushed to the frontier, and so that's the one that gets ionized. And we see that it takes a bit longer than I would like normally. It takes 21 steps to converge the core ionized calculation, but it does so without too much trouble, as shown on the relevant sections of the output file on the right. Finally, we use these core ionized orbitals to compute the ROC's core excited state corresponding to an excitation from the 1s to 3p level. Similar to before, we have SCF algorithm SGM, SCF gas read, where we are reading in the previous core ionized jobs orbitals. And then we again have reorder MO. This time we don't have to move the whole because we had previously moved the second orbital to the frontier. So this orbital 8 now is the carbon 1s. However, we need to move our target virtual orbital, the particle orbital, to the frontier. So we moved 11 right next to 8 and pushed 9 and 10 further out. And then we have ROC's true in order to make it run a ROC's calculation. And finally, we need a transform read such that it reads the previously saved orbitals to compute the transition dipole moment. And we toss this, we make this run, and we converge onto an excited state energy and transition dipole soon afterwards. So as a practical point here, I thought I would just say a few things about reorder MO. In that it is critical for specifying the initial gas configuration for restricted open shell DFT or ROCs. The way to think about reorder MO is that you should order the orbitals as the doubly occupied levels first, then the singly occupied levels, and finally the empty levels in that order. And we just need to specify up to the highest numbered MO that is out of order. Anything beyond that, which are in usual order, like 100, 101, 102, 103, don't need to be specified as long as there isn't a break in the pattern in that regime. For a ROC's calculation, basically, the whole point of reorder MO is to make sure that your hole and particle, your hole is placed in the original position of the HOMO, and your particle is placed in the original position of the LUMO, and ensuring that all the orbitals in between are shifted in a position corresponding to their occupation, whether that's double or unoccupied. For instance, in that formaldehyde excitation, if we had just skipped the coronization step and tried to do that directly, then our hole would be the ground state orbital 2, and our particle would be the ground state orbital 11. And so we would do sort of a reorder MO in which we push orbital to the HOMO and orbital 11 into the position of the LUMO, and everything else that gets moved out of order has to be explicitly written down, such as by having the 9 and the 10 out here. Yep. And one other point here, a practical point here, is that if you're trying to do some kind of a core level calculation using any of these orbital optimized methods, it's absolutely essential to make sure that your core hole is localized onto a single atom. Canonical MOs are delocalized over symmetry equivalent atoms in a molecule. Like in N2, your core levels are going to be a symmetric and antisymmetric combination of the 1s orbitals of nitrogen. However, the actual hole in these calculations need to be localized into a single atom. Otherwise, you'd get pretty massive delocalization error, as shown in table 2 at the bottom. This localization can be done by using that mixed basis approach. If you just specify one of the atoms to have a bigger basis than the other, then the symmetry is broken and the core orbitals would spontaneously localize due to loss of symmetry. Or you could use the electric field via multiple field to break symmetry and thereby localize core holes. It's a good idea to check whether your core hole is localized or not via visualization of orbitals with GUI2 in the REM for the core ionization step. If your core hole is not localized, then you probably need to change some stuff to make it localize and go so that you have a meaningful answer. And some last practical points, I guess, would be that it's strongly recommended to do a core ionization calculation prior to any excitations calculations instead of directly attempting to excite an electron from the core to an unoccupied level. It might seem like some wasted effort in converging the core ionized state, but trust me, it's very much worth the effort because the core hole formation is very much decoupled from the rest of the problem, and having the unoccupied orbitals of the core ionized state are a much better guess for the particle level of the core excited state than the unoccupied levels of a fully neutral molecule. Another thing is that for any of these core level calculations, you need a uncontracted or covalent separated basis set of at least triple zeta quality, like OGCC PCVTZ for the atom of interest. For everything else, you can again cheap out and use some double zeta basis. Whether you use augmented or not depends on how much you care about your Rydberg states. But for the site of interest, you need to use a high quality basis of at least triple zeta quality. Thankfully, it's just one atom for any calculation, so it doesn't really increase the cost all that much. And one of the good things is that core excitation energies generally have that, as I noted, something like a 0.1 eV uncertainty. So you don't need to have ultra tight energy convergence for single point calculations. You just need to converge to something like 10 to the minus 4 or 10 to the minus 5 Hartrees instead of 10 to the minus 8. This is of course only true if you don't want to do force or frequency evaluations. If you do any of that, then you would really need to converge your orbitals pretty tightly. And more guidelines are listed in some of these papers that we have written before, the JPCL 2021 for closed shell molecules and JCB 2020 subsequently for open shell systems. And if you want to do any relativistic calculations, just specify rel_x2c true in the REM section and it'll be automatically taken care of. And finally, to just summarize this whole rant, if you're thinking about ways to model an excited state that you have for a large system, your choices basically boil down to using either linear response TDDFT or ODFT. However, TDDFT has some issues. You don't have double excitations, CT states are troubling, you can't handle core hole relaxation, and therefore need to use massive empirically shift your XIS spectrum to have any kind of agreement with experiment. However, with ODFT, all of these problems are gone. The only problem is that you have a somewhat more temperamental and difficult to control method like a dragon, which well, kind of summarizes the approach in a way. And the conclusions as written down in a more formal form is just that ODFT is effective for many of these excited state problems where linear response fails, and square gradient minimization offers a reliable way to optimize these excited state orbitals by being an analog of ground state GDM through direct extremization of energy. And the cost of doing SGM for excited states is only 2 to 3 times as much as ground state GDM per iteration, although you'll need more iterations than a normal ground state calculation. With all of this, you can use ODFT to look at fun problems like charge transfer or Rydberg states or double excitations, and especially core excited states, where at least it seems like the scan functional yields semi-quantitative results versus experiment, leading to spectra and energies that can be directly compared against experiment without having to do any sort of post-processing, and thus help reveal what is actually going on there. And all of this is already in the QChem 5.4 release and written up in the manual. I'd be delighted to help if you run into any kind of issues, as my email's just given below. And I would just like to thank all the people who have made this possible. Professor Martin Head-Gordon for being a great advisor who has encouraged me to work on this. Troy Van Voorhis for first introducing me to rocks and this whole excited state ODFT methods in the first place. Eric Noskeman for fun and useful discussions. My co-workers, Dr. Yueji Mao, Leo Cunha, and Richard Kang, along with the experimental collaborators who always give me fun problems that poke my brain out. And thank you all for your attention. These are again the associated references if you are interested.
Thank you for this interesting and informative talk. We got a couple questions, and so just remind you that if you have question, you can use the GoToWebinar question box and submit your questions. So our first question is related to transition moments. Could you elaborate a little more on the calculation of transition moments, and have you benchmarked this, and also does it work with does it also work for MOM delta SCF or only work for rocks?
So for the transition moments, yeah, let me go back real quick. Yeah, so for the transition moment calculations, what I wind up doing is that there is some kind of an excited state wave function sort of in terms of the Kohn Sham Slater determinants. For rocks, it would just be a linear superposition the equal superposition of these two states. And once you have this sort of a state converged, you can just compute the transition moment between this two determinant excited state fake wave function and this ground state Kohn Sham determinant. And that would give you a transition dipole. And that seems to work fairly well in practice, looking at some of these excited states, well, at least the core level spectra that have come up. And a similar approach should work for delta SCF. If you look at this first peak here, that's not a 3-electron recoupling, that's just a plain delta SCF excitation. And there was also an interesting paper, I think last year, by Fred Manby's group that had looked at delta SCF transition dipole moment qualities, and they found that they were comparable to TDDFT. So this approach in general does, if I understood the question correctly at least, basically this approach involves computing the using the fake excited state wave function and the fake ground state wave function, AE the stated determinant, and then computing the transition dipole moment via orthogonal configuration interaction between them.
Thank you. So our next question, is there data for valence excited states like the CT states?
Valence excited states like CT states, well, not the TDDFT stuff I would say counts because they are valence excited states. Oftentimes they are in fact the lowest excited state of the molecule. So that would be the most obvious case of valence charge transfer excited states I can think of. I believe there has been a recent mountaineering database of charge transfer states that we are planning to look at sometime soon to see how that fares. In general, this sort of becomes a function of how long the distance of charge transfer is. If the charge is moving over only a very tiny distance, then it's functionally valence and nothing really matters. And if it is very long, then at that point it's just EA based problem. So like the Goldilocks zone of interesting charge transfer is surprisingly limited.
So our next question, how do DFT energies compare to the ones obtained employing linear response TDDFT using RSH functional for long range charge transfer?
So this is actually an example. Omega B97 X-V is a range separated hybrid. There's also CAMB 3-lip, which is I guess a classic range separated hybrid. And the answer is not really that great, but it also sort of depends. Like if I looking at the Hartree-Fock result, it's easy to see that you can have some kind of a range separated hybrid where you rapidly go to 100% exact exchange where you get systematic overestimation. And you can definitely have a tuned functional that'll agree perfectly. But if you just pick a widely used ground standard range separated hybrid, chances are it will be problem sensitive, but there's no guarantee that it will be good without something like without having to do explicit optimal tuning or something of that nature.
Thank you. So next question, and you mentioned that excited states are usually saddle points in the space of orbitals, which are actually unstable, but in general, can then also be local minimums?
Yep, there can be some local minima. Let's see. I guess the easy example is that if we restrict our attention to the manifold, or like if we forbid any sort, or rather, how do I phrase this? If we constrain this multiplicity, the M sub S of our problem, then, for instance, the lowest triplet state is a local minimum in orbital space, because it's within the triplet manifold. Now, if we start letting the spins rotate, as in with the GHF type calculation, we can make that collapse onto a closed shell ground state. But depending on the constraints available, you can certainly make some excited states be local minima. Just in general, that's not always general. That's not the case. But you can make some of them be local minima. And I think even without having to invoke any of this, there are a few that would be specifically local minima, but because they are the lowest for a given symmetric or related constraint.
Thank you. And the next question is from Agrestin, and thank you for your passionate seminar. As a prospective PhD student, I'm curious about how you could decide to delve into your topic. What makes you be dedicated to those methods, and is there any strong motivation or curiosity?
Honestly, this was not what I began with when I started grad school. I just fell into it because I had a lot of friends who worked on related methods, and just chatting with them a number of times made me think that, oh, this would be worth a look. So I guess my philosophy has mostly been to just keep on talking with people, see what is fun, and if that starts looking interesting, delve into it. And I mean, the way I keep myself motivated to work on this recently is just by talking with my experimentalist friends who do a lot of X-ray spectroscopy, and they always seem to have something interesting where I could be of help. So that automatically keeps me on my toes, so to say. Thank you. That was a very interesting question.
Thank you. So we have a question probably related to the previous one about the long-range TDDFT calculations, and is the PES accurately described using the OODFT? I think is the potential energy service actually described using the OODFT?
Yeah, it is. Yeah, it is, because then you just have the standard electrostatic interactions between the particle and the hole, giving that 1/r behavior. Because you're no longer tied to relying on orbital energies or something of that nature. You just have plain electrostatic interaction between the charges, and that indeed leads to the correct asymptotic 1/r behavior. I think Peter Gill in the IMOM paper explicitly showed this with some examples.
Thank you. Looks like we don't have more questions here. So if we have, first, I would like to thank you, Dave, for this wonderful talk again. And also want to thank attendees for listening. If you have questions later, feel free to shoot us an email or post your question on the talk forum, QCAN talk forum here.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.